Word up, followers! All right, how we doing, folks? Getting into this chapter 10. I don't want to waste any time because we're doing the impossible, what you might think is the impossible. 2 chapters in 1 week. Here we go. Let's do this thing. So I love these chapters here at the very end. We're going to really kind of synthesize everything we've been talking about and apply it kind of to the real world, to big picture stuff. So in chapter 10, what we're starting here with is intermolecular forces. Okay, so this is what we're doing. Okay, so what we have done up to now is intramolecular forces. Okay, so let's talk about those differences. So intramolecular forces are the forces within a molecule. So that's what keeps an electron attracted to a proton, for example. It's also, when we talk about intramolecular forces, this is what the force that 2 nuclei exert onto each other in a chemical bond, okay? So forces within a molecule. What we're going to get into in this chapter is intermolecular forces, IMF, intermolecular forces. Those are the forces between molecules, okay? So for example, if I have 2 neighboring water molecules, let's say, okay, I'll draw another one up here. We know the intermolecular forces are the forces that keep all of these atoms bonded to each other. That's the intramolecular forces. The intermolecular forces are the forces exerted between 2 neighboring water molecules. They're the forces that keep those molecules together in a liquid or a solid, for example. Okay? So now if we look at kinetic energy of these molecules versus their intermolecular forces, or sometimes we call the interactive forces synonymous with the intermolecular forces. So this means the forces that 2 neighboring molecules experience, right? So if we look at like an ice cube, okay? Those molecules are really close together, right? In a solid, and all solids they are. So we would say the molecules themselves have the lowest kinetic energy, but the highest interactive forces. So the molecules are glued to each other in a way, okay? In a liquid, that becomes intermediate. So in a liquid, the molecules are more free to tumble around and move. They adopt the shape of their container. And see how I can slosh this water around, right? I'm really happy I didn't spill that on my keyboard. There's intermolecular forces keeping those water molecules connected. However, because it's intermediate, I can slosh them around, right? They can move around a little bit. In a solid, I can't really slosh a solid around, right? It maintains its crystalline structure. And of course, in a gas, these molecules are the furthest apart. Gases are not very dense, right? The molecules are really far separated. They have an enormous amount of kinetic energy. They're moving around, they're colliding with each other. And their interactive forces are therefore the lowest. So it's really all about how close neighboring molecules can get to each other. The closer they can get to each other, the stronger are their interactive forces or their intermolecular forces. Okay? So there's several types of intermolecular forces we're going to talk about, and I'm going to go through them one by one in this lecture. Okay? The first one to discuss are dispersion forces, and specifically, we call this London dispersion forces for the gentleman Fitz London, scientist. So the force between nonpolar molecules caused by the presence of temporary dipoles. And I'm going to discuss momentarily here how this temporary dipole manifests. However, the main thing to recognize with London dispersion forces, LDF, This is principally the force that exists between non-polar molecules. That's the key word there. So when you think LDF, London Dispersion Forces, think non-polar. Okay, so the London Dispersion Force or forces can induce something called a temporary induced dipole. And that separation of charges produced in an atom or molecule by a momentary uneven distribution of electrons. And by momentary, we're talking about teeny tiny fractions in time. So for example, let's suppose we have two H2 molecules. So here's an H2 molecule and here's an H2 molecule. And they're on a collision course with each other. So when they're really far separated, they have virtually no interactive force between the two. It's as if they don't even know that each other exists, okay? And as they get closer, these interactive forces become much more important. And what can happen is there's electrons. So if you recall from our Chapter 9 discussion, I showed you this really cool simulation of an H2 molecule. And this sphere represents, I'll say that's the electron density. So we know that that's the hybrid orbitals. But we can basically think of this sphere as electron density. Okay? So as this molecule A gets really close to molecule B, the electrons that are surrounding this molecule are repelled by the electrons in the neighboring molecule. All right? And because they're repelled, what ends up happening is all of the electron density moves. Okay? It kind of moves out of the way. Much like if you go and you're about to collide with somebody walking down the street, you might kind of like move out of the way a little bit, unless you're like a sadomasochist and you want to like body check somebody. Anyways, so these electrons, they kind of feel the negative charge from the neighboring molecule. So they all move over to the other side of the molecule, leaving this side of the molecule partially negatively charged, which leaves the other side of the molecule partially positively charged. And then as molecule B gets closer to molecule A, that induces temporarily the same type of dipole moment. And so this is not so important in gases. However, in liquids, in non-polar liquids, right, there has to be some kind of glue holding those molecules together in the liquid phase. And it's these London dispersion forces, where as they get close to each other, they can induce these temporary dipole moments, okay? And the effect of this London dispersion force scales with the size and number of electrons of an atom or molecule, all right? So for example, we'll use boiling point as a metric for LDF. And so what that means is the higher the boiling point of something, the stronger is its intermolecular forces, whether it be London dispersion or another type of force we haven't discussed yet. Basically, the temperature at which something boils is a very good indicator of how strong its intermolecular forces are. So for example, helium boils at a whopping 4 Kelvin. So that means above 4 Kelvin, helium is a gas. You have to cool it down very, very low to 4 Kelvin to get it to liquefy. That means helium has very weak London dispersion forces, incredibly weak London dispersion forces. However, if we go all the way up to like xenon or radon or something like that, look at this, the boiling point is humongous, okay? And if you note here Z, so that's our nuclear charge, right? So that tells us how many protons it has, and correspondingly for a neutral atom, how many electrons it will have. Look, 54 electrons on xenon. There it is, right? 54. So this temporary induced dipole moment on xenon is quite noticeable. The fact that it boils at 165 Kelvin, or even for radon, 211 Kelvin. And similarly, if we look at the halogens, even though they're not atoms, they're molecules, but they are still non-polar molecules, so they exhibit London dispersion forces. If you now look at what happens to these things, I mean, fluorine, 85 Kelvin. Okay, so we could say fluorine's intermolecular forces are fairly weak. But look at chlorine. I mean, 239 Kelvin. 239 Kelvin is like minus 30 Celsius. And even when you get to bromine, this is amazing. That's a boiling point that's greater than room temp. So Br2, I don't know if you knew this or not, but bromine is a liquid at room temperature. And 332 Kelvin, that's a really large boiling point for a nonpolar molecule. And then if you go to iodine, iodine is actually a solid at room temperature. It has such strong London dispersion forces, okay? And so again, this is all about the size of the atom. The bigger these atoms are, the more electrons, the more protons there are, and the more this temporary induced dipole moment, the stronger it becomes, which is basically a way of saying the bigger a nonpolar molecule is, the stronger are its London dispersion forces, okay? So let's move forward. So now we can talk about London dispersion forces with a little bit more complicated molecules. So this is the series of hydrocarbons. And if I start here with butane, butane is, oh, I'm going to have to think quickly on my feet, C4H10, okay? Pentane is C5H12. I think I did that right. 2, 4, 6. Yep, I did that correctly. Hexane is C6H14. Heptane is C7H16. And of course, octane is C8H18. So we're increasing by one carbon at a time. And here I've got the normal boiling point. I'm going to define for you later on what we mean by the normal boiling point, okay? But if you notice here, butane, it boils at negative 0.5 degrees Celsius. So those of you, you smokers out there and your butane lighters, right? You notice that there is liquid butane in there because it's under pressure. And we'll talk about that as we go, that we can force a gas to be a liquid at high pressure. But all the same, as soon as you release, you push that little light thing, you hear the gas, psst, you hear it hiss off, right? So it's gasifying as soon as you release its pressure into the atmosphere. And you notice when you add one carbon and consequently two hydrogens at a time, it has a really significant effect on the boiling point. To the point where you get to octane or heptane, which even have comparable boiling points to water. I mean, octane even boils much higher than water. And so I'm going to talk about this. There's another effect that's going on there as well, which is the shape of these molecules. But as you can see here, where their molar mass is increasing, where I'm adding basically more electrons and protons, the boiling point increases. And it's due to the London dispersion force. Okay, moving on. So, shape is very much important to dispersion forces, okay? And this is in part why you see such a huge jump in boiling point for octane and heptane, because as it turns out, these molecules are kind of like little spaghetti noodles. A C8, it's fairly long, and it gets long enough to the point where it can kind of like a spaghetti noodle tumble over other octane molecules. So if you imagine each one of my fingers is like an octane molecule, right? When it gets near other octane molecules, they can get tangled up with each other, right? And that makes them really hard to separate because once they get tangled up, their intermolecular forces are incredibly strong. In fact, stronger than water. Water boils at 100 degrees, octane boils at 126, okay? And this is also gives us a property that we often call greasy. So these molecules are very greasy or oily, and that has to do with their shape. The fact that they can get tangled up with each other But now when you have another molecule on top of that, it just slides right off, because something like water or another molecule doesn't necessarily want to get in there and break up that, that network, that intermolecular force network. So it makes them very greasy. Okay. So if we look now at the series of C5s, so pentane is a C5, 2-methylbutane is a C5, and 2,2-dimethylpropane is a C5. So in other words, 1, 2, 3, 4, 5 carbons in each of these molecules, but with different bonding patterns to give us a different shape. Okay? So you notice here this molecule 2,2-dimethylpropane, and by the way, you don't have to know how to name these. That will be what you do in organic chemistry, for those of you that take that class. You notice here that this one is just kind of shaped more or less like a sphere, right? We can say that this carbon here in the middle, that's an sp3 carbon, so it's going to be a tetrahedral. But then look, there's other tetrahedral carbons as well. So this thing is really like, it's a tetrahedral of tetrahedrals, but we can approximate its shape as a sphere, right? And now if you look at 2-methylbutane, it's almost linear, but it has one branch. This is what we call this. And then if you just look at pentane, it's just a straight linear molecule. And now look at their boiling points. So the straight linear molecule, what we would call normal pentane, boils at the highest temperature because of the way it can tangle up with itself. Okay? These other isomers of pentane, these other C5s, because they're like these balls, right? When they pack together, there's going to be empty space, right? Much like if you imagine a jar full of M&Ms or jelly beans or something like that, right? They don't pack together with uniform efficiency. On the other hand, if you imagine like a jar of spaghetti noodles, right? They pack together really, really well. Okay, so shape is also important to dispersion forces. Even though these all basically contain the same number of carbon atoms, the shape can also dictate its physical properties, such as boiling point. Okay, moving on. So let's see here. Let me review a learning goal. Okay, so we did, and so I'm going to cancel some of these just so you're aware. In the interest of time, we're not going to do this full chapter. So understand what intermolecular forces are, including London dispersion, temporary induced dipole. Okay, so we've done that, but now we haven't done ion dipole, dipole-dipole, dipole-induced dipole, and hydrogen bonding. So we've got to get into that, okay? So our ion dipole interaction is an attractive force between specifically an ion and a molecule that has a permanent dipole moment. So ion dipole, right? It's between an ion and a molecule with a permanent dipole. And then the sphere of hydration is, so specifically now, like in our ion dipole interaction, if let's say we're talking about water and all of the commonly occurring ions that we might expect to be in water, we create something called the sphere of hydration, which is a cluster of water molecules surrounding an ion in aqueous solution. And this cluster is due to the intermolecular forces that exist not only between the water molecules and the ion, but also between the water molecules and the water molecules themselves. Okay? So for example, if we look at sodium here, and I'll remind you that our water molecule has this bent geometry, right? Where it's partially negative on the oxygen side and partially positive on the hydrogen side. Water will surround itself such that the oxygens are pointing towards the cation, because the oxygen is partially negatively charged and the cation is fully positively charged. Okay? So that's our ion dipole interaction. But now if we look, and we would call this a hydrated Na ion, because that sodium plus ion is not like naked or anything like that, right? It's surrounded by water molecules, And as that ion moves through solution, those water molecules travel with it. Okay? So the hydrated anion, so in this case a hydrated chloride, will be surrounded by water molecules, but this time with the hydrogens oriented towards the anions because the hydrogens are slightly positively charged and the anion is fully negative. Okay, so now as we imagine here, this simple network of molecules creates our inner sphere of hydration, okay, which is indicated here by this darker blue color, okay? We would have an outer sphere of hydration, which is the water molecules that are interacting with the water molecules that are interacting with the ions. And then finally, we have what we would just call bulk water. And we call this bulk water because it's as if the ions are not even there. So to these water molecules that are on the very outside, it's like they can't even feel that there's a cation there, okay? And as you might imagine, the more concentrated one of these solutions becomes in ions, the less bulk water we have, okay? So as we get into chapter 11, we'll talk about this when we have concentrated solutions of ions. There's some very interesting properties that manifest, namely osmosis, as well as boiling point elevation and freezing point depression. So we'll talk about that soon, okay? So let's move forward here, okay? And more discussions of interactions amongst polar molecules. So here's a thought example that I want you to kind of think about on your own for a moment. So maybe pause the video for a second, but I'm just going to move right past this. So if we look at these two molecules right here, okay, 2-methylpropane and acetone. If we look at 2-methylpropane, it has 1, 2, 3, 4 carbons. So that's a C4. Acetone, on the other hand, only has 3 carbons. So why is it that acetone boils much higher than 2-methylpropane? So think about that, okay? Did you think about it? Did you pause the video? Maybe you already have the answer in your head. I'm going to keep moving forward. So the answer is the dipole moment in acetone. It's much, much stronger than the lack of dipole moment. I mean, you might be looking at this and say, well, this molecule is not symmetrical, so it should have a dipole moment, and that's true. But the dipole moment of this molecule will be incredibly weak because carbon and hydrogen don't have a lot of difference in their electronegativity. However, carbon and oxygen, right, there's a big fat dipole moment that exists between that carbon and oxygen as indicated here in this picture, right, where it's partially negative on this side and partially positive on this side. So that means neighboring acetone molecules, I'm going to use the shorthand notation of drawing this molecule. So that means neighboring acetones can line up like this, right? They're lining up with their dipole moments all in a row like soldiers in a line, okay? And that keeps them stuck to each other quite well, okay? Even so, acetone boiling at 329 Kelvin, that's like 50 some odd degrees Celsius. So it's not a large boiling point per se. But all the same, it's significantly larger than 2-methylpropane's boiling point because of this dipole moment, all right? Okay, so we have so what I just described there with acetone is what we call the dipole-dipole interaction. So an attractive force between polar molecules, and the dipole moments will line up. So for example, take water, right? So we can see in a network of water molecules, they will always be aligned, oxygen, hydrogen. I could draw another one right here, right, where that dotted line is showing you that interaction, that intermolecular force interaction, okay? And as it turns out, the dipole-dipole interaction is incredibly strong. And we have a special name for this type of interaction, specifically when it involves hydrogen. And I'll talk about that next. Okay. So we have another type of interaction, the dipole-induced dipole interaction, and it is exactly what you might think it is. It's an attraction between a polar molecule and the oppositely charged pole it temporarily induces in another molecule. So for example, if we look at water and oxygen, as it turns out, interact quite strongly, okay? And the reason for that is because as a water molecule gets close to oxygen, it can do this thing, right, where the negative end of this molecule, makes these electrons move to the opposite side temporarily in the oxygen and creates this dipole-induced dipole. So why is this important? Well, as it turns out, if we imagine like a jar of water, and maybe there's like a little fish living in this water. So this is my terrible drawing of a little fishy, okay? Fish breathe oxygen underwater. Where does that oxygen come from? Well, it can get taken up into the water. And as it turns out, oxygen is very water soluble. Oxygen as a gas can remain in liquid water sustainably, okay, for long periods of time. And that's because of this dipole-induced dipole interaction. Because as oxygen is getting taken up, and oxygen gets taken up into water through little like actions like this, right? So those of you that are, maybe you have a fish tank, you know that if you agitate the surface of your water, it can influence oxygen to get taken up. Or if you just have a pump in your fish tank, right? If you just pump air straight into the water, that oxygen will stay in the water for a considerable amount of time because of this dipole-induced dipole. And of course, in natural waters, in the ocean and rivers and streams, when the surface of water is agitated through either waves or ripples or like a rock falling in the water, that influences air to get bubbled into that water, okay? So let's see here. So specifically, when we have the dipole-dipole interaction, so we'll say dipole, oops, I can't spell it all, but you already knew that. The dipole-dipole interaction with hydrogen and look at this, oxygen, nitrogen, and fluorine only. We call this the hydrogen bond. And it's important to note this is not an intramolecular hydrogen bond. This is an intermolecular hydrogen bond. Okay? So if we look at acetic acid, for example, acetic acid can make these beautiful dimers, two of them, right? That's all a dimer means. Two pairs, or one pair, I guess. A trimer, would be 3. A tetramer would be 4. So these types of molecules can make these lovely dimers because of the way they're both trigonal planar here in this carbon, this sp2 carbon. And they just line up so well. Like, look, it makes this lovely hexagonal shape, right? And so this dotted line right there, that's the hydrogen bond. And as it turns out, it's quite strong. It's incredibly strong. But it's also important to note, look, that this is hydrogen with only oxygen, nitrogen, or fluorine. So you can't make a hydrogen bond with hydrogen and carbon, or hydrogen and phosphorus. It's really only observed in oxygen, nitrogen, fluorine only. So this is all over the biological world. The hydrogen bond is incredibly important in biology. In fact, the hydrogen bond is the glue that keeps DNA strands together in the double helix pattern, right? So for example, if we look at some of these DNA residues, okay, adenine, thymine, guanine, or cytosine, right, A, T, G, or C, they are zipped up. I mean, you can take an RNA strand, which is one single DNA, right, one single strand, and another RNA strand, and they can just zip together like a zipper with the hydrogen bond. So for example, if we look here at adenine here, there's this amine group, this NH2 group, right? So that contains a hydrogen, and it can do a hydrogen bond with a neighboring thiamine with that hydrogen interacting with the oxygen. And so this becomes really strong now because it can also do another hydrogen bond on the other side of the molecule, where now this amine group, this NH group, here is interacting with this other nitrogen right here. So there's a hydrogen bond between hydrogen and oxygen and between hydrogen and nitrogen. If you look at guanine and cytosine, there's actually 3 hydrogen bonds between G and C that can get created. And again, it's important to note, this is not an intramolecular bond. This is not like covalent. They're not sharing electrons. It's just the mutual attraction of oppositely charged things. Hydrogen is slightly positive. So hydrogen, we'll say, is slightly positive, and oxygen, nitrogen, and fluorine are slightly negative. When they get close to each other, opposites attract. It keeps DNA glued together. So there's also some amazing examples of hydrogen bonding in water that I'll describe as we get to the end of this section. Okay. Oh, never mind. It's right here. Okay. So I'll talk about the hydrogen bond in water right now, but then I'll talk about some of these amazing properties at the very end. Okay. So as it turns out, hydrogen bonding in water is amazing. It's what gives snowflakes or ice crystals their unique, what we call dendritic structure. So in ice, these hydrogen bonds, right, they're lining up from hydrogen to oxygen, and look, it makes this lovely hexagonal pattern. And so when you multiply that by a mole, right, imagine now a mole of these patterns. This is what gives you that really cool looking snowflake pattern, that snowflake crystal. And of course, no one snowflake is the same as another snowflake because occasionally this network gets disrupted, right? It's not a perfect hexagon all the way through, right? Occasionally there are other ions that get embedded into that water crystal structure or other organic molecules that get frozen with the water, right? And what becomes interesting when you melt these things, so water as a liquid, you know, it's constantly tumbling around like other liquids do, as I demonstrated right here, right? So these hydrogen bonds are constantly breaking and reforming as water molecules want to move around in this liquid phase. And as it turns out, that's strong enough that when I slosh it around, look at how the water can like rise up, right? It rises with itself. So when you slosh a liquid around, those molecules are dragging other molecules with them to the point where the whole damn thing acts like one continuous fluid. In fact, that's why we call it a fluid, right? Because it can adopt the shape of its container. Okay, so the last thing that I'll summarize here, or a couple more slides to summarize. I know this is going a little long. If we look at now the trend of polar molecules on their boiling point and the trend of small polar molecules on the boiling point, okay? Water is a huge exception. And in fact, so is HF and NH3. So before we describe the exceptions, let's just look at the normal pattern. Let's look at methane. Non-polar molecule, right? There it is, carbon. So all of what we're going to do is start at all the various groups. So you notice group 2, 3, 4, and 5. So groups 2, carbon, silicon 3, germanium 4, tin 5. And look, you notice that there's a nice increasing trend as we increase the number of electrons and protons in that central atom. Look, CH4, SiH4, GeH4, SnH4. Boiling point increases as we would expect. But now if we go to the next series, so we just did carbon, silicon, germanium, tin. Now let's go to the next series. Nitrogen, phosphorus, arsenic, and, oh my God, I've totally blanked out, shamefully. I'll think of it. Antimony. Yes, antimony. So notice now NH3 is a huge exception, right? And the reason for that is because nitrogen, so we know that it has this structure, but so will these other molecules, right? pH3 will have the same Lewis structure. ASH3 will have the same structure. SpH3 will have the same structure. So why is NH3 now such a huge exception? It's because of the size. NH3 is sufficiently small. It's very small. And what that means is it can pack together with other NH3s quite well. And so the same thing is observed with HF, and the same thing is observed with H2O. So these are all very small. All of these, H2O, HF, NH3, and that makes them incredibly polar. And also, maybe you've thought of the other thing, hydrogen bonding, right? Hydrogen bonding is only observed between oxygen, fluorine, and nitrogen. So not only are they very small, they can pack together very well, but they're capable of hydrogen bonding with themselves. So that makes them exceptions for this trend in boiling point. And as you notice right here, if we look at like HCl and HBr, you know, there's a little bit of an exception, like a minor exception right there. But for the most part, like HCl, HBr, HI, they all follow the trend. H2S, H2SE, H2TE, it follows the trend. But because of size and hydrogen bonding, H2O, HF, and H3 are exceptions with this boiling point trend. Okay? So summarizing this, so this was a big lecture. So summarizing all this stuff, as far as relative strength, ion dipole is definitely the strongest. Okay? So like when a water molecule, for example, is interacting with an ion, that's quite strong. Okay? And I didn't really talk about these phenomenon that's in this chart, but I'll talk about that as we go. Hydrogen bonding. So I just want to use this chart to talk about order of strength. Okay? Hydrogen bonding is the second strongest. And in the absence of any ions, hydrogen bonding will be the strongest, right? If you're talking about systems where there are no free ions, hydrogen bonding is usually the strongest. Okay? However, of course, if we have ion-dipole interaction, that wins out. So the dipole-dipole is third. Okay? And so we talked about that when we compared the dipole moment, or the boiling point of acetone to that 2-methylbutane, I think the molecule was. So the dipole-dipole interaction is very strong. Dipole-induced dipole is in fourth place, and then in fifth place is the dispersion force. Now, what's interesting, though, about this dispersion force, I'm going to show you some examples later on. The dispersion force can actually become incredibly strong when the molecules are quite large. For example, I showed you that octane, which is nonpolar, it can only do dispersion forces. It has a boiling point of 126 degrees. Water only has a boiling point of 100 degrees. So we have to take these, this relative order of strength, we have to take it with a grain of salt, pun intended, because we know that there are these competing effects like shape, mass, hydrogen bonding, etc. So in general, this order holds through most things, although of course we know that chemistry is the science of exceptions. So a general understanding of this is sufficient for this class. So let's talk about the learning goals from this video. So we definitely did this number one. Let me get my highlighter. Understand what intermolecular forces are, including London dispersion, temporary induced dipole, ion dipole, dipole-dipole, dipole-induced dipole, and hydrogen bonding. Okay. Be able to explain the effects of intermolecular forces on boiling point and predict trends in boiling points for small molecules. So, basically recognize hydrogen bonding, that creates an exception for small molecules. Otherwise, the trend scales with their mass. The higher the mass, the higher the boiling point. So understand how polarity and solubility are affected by intermolecular forces. So that's where we're going to go next. Okay. All right, folks. Thanks for watching.